1938. Almost every railroad boss in America dismissed EMD's new two-stroke diesel as too crude for serious service. Yet within just a few years, that overlooked engine, the 567, would make mighty steam locomotives obsolete almost overnight. Not through brute power, but by rewriting the rules of uptime, economics, and standardization. Why did so many experts get it wrong? The answer begins in a LaGrange factory with a gamble nobody else dared take. On a gray October day in 1938, the factory gates at LaGrange, Illinois, swung open to reveal something the American railroad industry had never seen. The new EMD locomotive, powered by a pair of freshly built 567 engines, rolled onto the shop tracks. The design was radical. Two-stroke diesels rather than the massive, hissing steam giants everyone knew. Factory engineers and a handful of executives watched as the locomotive idled, its distinctive exhaust note echoing across the yard. Word spread quickly. Some railroad men scoffed. The old guard called it a gamble, even a folly. But the leadership at EMD saw what others missed. The future of railroading depended not on tradition, but on machines that could run longer, cost less to maintain, and return to service faster than anything steam could offer. The press took notice too. Railway Age and other journals reported on the debut, noting the boldness of EMD's approach. The 567 engine, named for its 567 cubic inches per cylinder, was built from scratch for railroad duty. No shortcuts, no borrowed designs. As the locomotive idled on the tracks, the stakes were clear. If this engine could deliver on its promise, it would rewrite the rules for every railroad in America. Two-stroke. Diesel engines had a reputation for being rough, noisy, and unreliable, traits that railroad men saw as deal-breakers. The engineering journals of the late 1930s were filled with warnings that two-stroke designs were considered too crude for serious railroad work. Four-stroke designs, with their precise timing and measured cycles, were the accepted path. EMD's decision to ignore this orthodoxy was seen as reckless. Competitors and industry veterans lined up with familiar arguments. Two-strokes, they said, belonged in outboard motors and farm equipment, not in locomotives pulling freight across the continent. The skepticism was not just technical, it was cultural. Steam had set the standard for a century, and even diesel advocates preferred the supposed refinement of four-stroke engines. EMD's engineers faced open ridicule from some corners, but behind the scenes, they were betting on something the critics did not see: the relentless demands of railroad duty. Railroads did not need elegance. They needed engines that could deliver power every single crankshaft revolution, day after day. The risk was real. If EMD's gamble failed, it would not just be a technical setback. It could mean the end of their ambitions in the locomotive business. Every test run, every hour on the dynamometer carried the weight of that risk. Inside the EMD 567, every movement of air is choreographed with mechanical precision. As the piston drops, it exposes a row of intake ports cut into the cylinder wall. At that instant, a blast of fresh air, pushed by a Roots blower, spinning at twice the engine speed, floods the cylinder. This incoming air charge sweeps through in a single direction, forcing spent exhaust gases out through the exhaust valves set in the cylinder head. The timing is so exact that air and exhaust never mix, ensuring each bit of fuel is burned cleanly and efficiently. This process, known as Uniflow scavenging, is what sets the 567 apart from earlier two-stroke designs, which often left behind a tangle of unburned fuel and leftover gases. Here, the entire exchange happens in a fraction of a second, and it happens for every cylinder, every time the crankshaft turns. The result is a power stroke on every revolution, not every other one. That means twice as many bursts of energy, delivered with machine-like regularity. For railroads, this translated into engines that could pull harder and run longer without the sluggishness or unpredictability that plagued other designs. The 567's airflow choreography was not just a technical feat, it was the secret to extracting maximum power from every drop of fuel, mile after mile. With an 8.5-inch bore and a 10-inch stroke, each cylinder of the EMD 567 displaced 567 cubic inches, numbers that dwarf anything found under the hood of a car or truck. In its largest form, a 16-cylinder 500 packed a staggering 9,072 cubic inches of displacement. But raw size alone was not the point. The real breakthrough was how this engine delivered its power. Instead of chasing high engine speeds, the 567 was tuned to run at a steady 800 revolutions per minute. That's where railroads needed muscle, not for short bursts, but for hour after hour of relentless pulling. At 800 revolutions per minute, the engine could maintain maximum torque without breaking a sweat. This was not about racing from stoplight to stoplight. Locomotives needed to start a heavy train, get it moving, and then keep it rolling across hundreds of miles of track. The 567's two-stroke cycle meant every turn of the crankshaft produced a power stroke, doubling the work compared to a four-stroke engine running at the same speed. While competitors struggled to balance power and reliability, the 500's simply kept turning, day and night, with each massive piston doing exactly what it was built to do. For railroaders, the math was simple. More displacement at the right speed meant fewer breakdowns, longer runs, and engines that could shoulder the load without complaint. Turbocharging a locomotive engine sounds simple. Let exhaust spin a turbine, force more air in, make more power. But for the EMD 567D, the challenge ran deeper. Locomotive duty demands instant torque at every throttle notch, not just a rush of power at high speed. EMD's engineers tackled this by creating a turbocharger that did not wait for exhaust pressure to build. Instead, they linked the turbo directly to the engine's gear train with a mechanical drive. At low RPM, when a traditional turbo would lag, this gear-assisted setup spun the compressor as fast as needed, pushing air into the cylinders from the first turn of the crankshaft. As the engine picked up speed and exhaust flow increased, an overrunning clutch inside the turbocharger disengaged the mechanical drive. Now, exhaust gases alone kept the turbo spinning. The transition had to be seamless. A rough handoff would mean a sudden drop in boost, risking engine stumble or even damage under load. This clutch system was a marvel of timing and precision. But it added complexity. Failures could mean lost power, or, in the worst cases, catastrophic turbo damage. Yet the payoff was clear. Full torque from idle, no turbo lag, and horsepower that scaled smoothly with demand. EMD's gear-assisted turbo and clutch system set a new standard for forced induction in railroad engines, proving that innovation was not just about making things bigger, but making them smarter. A steam locomotive breaking down meant days, sometimes weeks, lost in the shop. Every major repair required teams of skilled craftsmen, custom parts, and a full teardown. The EMD 567 turned that reality on its head. Each cylinder became its own self-contained power assembly, a unit with piston, liner, cylinder head, and injector all bolted together. When a cylinder started losing compression or showing signs of trouble, mechanics didn't need to strip the whole engine down or wait for a machinist to fabricate new pieces. They grabbed a hoist, unbolted the faulty assembly, and lifted it straight out. A fresh, rebuilt unit, waiting on the shop floor, went right back in its place. The process could take as little as 4 hours, even for a 16-cylinder monster. For comparison, A major steam repair might sideline a locomotive for 2 weeks or more. The difference was staggering. A diesel engine could be back in service before the day's shift ended, earning revenue while steam engines sat idle. Shop crews who once spent nights wrestling with heavy castings and precision fits now worked with standardized modules and simple tools. The modular swap didn't just save time, it changed the economics of railroading. Every hour shaved off a repair meant more trains running, fewer engines sitting cold, and less money spent on specialized labor. The 567's design wasn't just clever engineering, it was a practical answer to the relentless demands of the railroad business. Railroad procurement teams, used to keeping shelves stocked with dozens of unique parts for each steam locomotive model, faced a new reality with the EMD 567. Whether locomotives ran with 6, 8, 12, or 16 cylinders, every power assembly was built to the exact same specification. That single design choice let a railroad stock one set of replacement parts for its entire diesel fleet, slashing inventory costs that once ran into the hundreds of thousands each year. Replacement parts and savings. Mechanics trained on one engine could service them all, cutting down on specialized training programs and reducing the risk of costly errors. Mechanics could move between assignments faster, and the chance of mistakes dropped. Instead of managing a patchwork of incompatible components, supply clerks ordered crates of identical assemblies, confident that each would fit any unit powered by the 567. For railroads operating hundreds of locomotives, this translated into real savings. Less capital was tied up in parts, fewer engines were sidelined waiting for the right cylinder or injector, and a maintenance workforce could move seamlessly from switchers to mainline freight haulers. Real savings. The 507's uniformity did not just streamline repairs, it created an economic moat around EMD customers, making it expensive and complicated to switch to a competing system. Uniformity and economic. The result was a network effect. The more locomotives with 567 engines a railroad owned, the more efficient each additional unit became. This was not just an engineering win. It was a business strategy that locked in loyalty and scaled profits with every new locomotive delivered. Network effect and loyalty. Railroad executives quickly realized that EMD wasn't just offering a new engine. They were selling a complete operating system. Every locomotive came as a bundled package. The EMD 567 engine, generator, traction motors, control gear, and a training program for mechanics and engineers. Field support teams followed the locomotives wherever they went, setting up service networks that stretched from Chicago to the smallest branch lines. This level of integration meant railroads could call a single number for parts, training, or troubleshooting. No more juggling vendors or waiting for specialized craftsmen. For the men running the numbers, it was a revelation. The cost of keeping a fleet rolling dropped sharply, and the headaches of managing a patchwork of incompatible systems disappeared overnight. Beyond economics, the 567 left its mark in ways that still echo through railfan culture. The sound that defines EMD diesels, the rapid, staccato exhaust, the deep chuff, the high-pitched whine, comes not from the turbocharger as many believe, but from the engine's very design. Two-stroke firing delivers a power pulse every revolution, doubling the exhaust cadence of four-stroke rivals. The Roots blower's gears add their own mechanical howl, and the exhaust valves snap open and shut with machine gun precision. Together, these elements create a signature that is instantly recognizable, even decades later. For railroaders and enthusiasts alike, the EMD 567 wasn't just a machine. It was a complete experience, engineered from the rails up to change everything about how American trains worked and sounded. Somewhere in the late 1960s, a new kind of engine swap began showing up in railroad shops across North America. Mechanics rolled out aging locomotives stamped with 567 builder plates. But when the cylinder heads came off, what they found inside did not always match the badge. Instead of the original 567 power assemblies, these engines were getting a quiet upgrade. 645 power assemblies designed for EMD's next-generation locomotives slotted straight into the old crankcases. The fit was not perfect, but it worked, enough to breathe new life into fleets that would have otherwise faced the torch. Railroads were not sentimental about numbers or names. They were hunting for more horsepower, better reliability, and fewer headaches keeping aging units on the rails. The 645 power assemblies offered all that, with improved liners, pistons, and injectors. For a fraction of the cost of a brand new locomotive, a railroad could get a power boost and parts compatibility with its newest engines. The hybrid 567 and 645 units ran stronger, lasted longer between overhauls, and let mechanics stock one set of spares for everything from first-generation F units to the latest GP38s. Today, plenty of locomotives still wear their 567 identity with pride, even though their hearts have been swapped. For preservationists and restorers, this creates a puzzle. What counts as original, and what is just a number on the side? For the railroads, the answer was simple. If it pulled trains and made money, it was the right engine for the job. Road switchers, passenger streamliners, and yard switchers, EMD's 567 engine powered them all. The same core design could be found in the GP7, hustling freight through the night in E-units gliding past mileposts at 100 miles an hour, and in SW series switchers shuffling boxcars through crowded yards. This adaptability was not just a technical curiosity. It meant that one engine family could handle every job on the railroad, from the heaviest mainline drag to the constant stop and go of switching duty. Steam locomotives, by contrast, were specialists. A mountain freight engine might be useless on a passenger express. Each class demanded its own parts, its own maintenance crew, and its own shelf of spares. Even with the best planning, a steam locomotive's day rarely ended without a visit to the roundhouse. Ash had to be dumped, fireboxes cleaned, boilers inspected, bearings repacked. Major repairs meant weeks out of service, with skilled craftsmen tearing down machinery built more like a cathedral than a truck. The 567 changed that calendar. A diesel could run for days between scheduled maintenance. If a cylinder started to fail, shop crews could swap it out in hours, not weeks. Service logs from the 1950s show locomotives spending more time moving freight and less time waiting for repairs. For the first time, railroads could count on a single design to keep trains rolling, no matter the assignment. Economic logic was inescapable. More trains running, fewer engines sidelined, and a workforce that needed less specialized training. The 567 didn't just replace steam, it made the old way of working impossible to justify. In the decades since their debut, EMD 567 engines have found unexpected second lives far from the main lines where they once reigned. Tugboat operators, faced with the harsh demands of harbor work, turned to retired 567s for their relentless reliability. In ports from the Gulf Coast to the Pacific Northwest, these engines power boats that push barges and guide ships day in and day out. Hospital backup generators, sawmills in remote forests, and industrial plants needing dependable power have all relied on the same technology that once pulled freight across the continent. Even as railroads moved on to newer designs, the 567's reputation for durability kept it in demand. Tourist railroads and heritage operators now care for these engines with a mix of pride and reverence. Locomotives built in the 1940s and the 1950s still haul passengers along scenic routes, their engines thumping with the same rhythm that once echoed through mountain passes and prairie towns. Mechanics who maintain these machines speak of them in almost personal terms, a testament to the bond forged over decades of service. For many, the 567 is not just a piece of history. It is living proof that thoughtful engineering can outlast the era it was built for, continuing to do real work long after the world has moved on. Decades after its debut, the EMD 567 still pulls loads and powers industries, proof that true innovation outlasts its disruptors. As railroads now face new transitions, from automation to decarbonization, the lesson endures. Adaptability outpaces nostalgia. In a world racing toward the next breakthrough, the engines that once ended an era remind us, survival always favors those willing to change. What do you think the next revolution will look like?